So this is chapter 2.1. We learn about the anti-power rule, where you take the exponent of x and add 1 over the exponent plus 1, and then plus c, which is to account for any constant that might have been there before the derivative was taken. And this next box is basically telling us that we can integrate separately over addition, but if there's a constant times a function, then we can take out the constant in front of the integral. And these are our derivative rules, which we should know for memory. Sine, cosine, tangent, others. And these are integral rules, which we should also know for memory. And then these are trig inverse integral rules, which we should also know.
So this is 2-2 integration by substitution, also known as U-subs. So this is basically the process of undoing the chain rule. So here are the steps. Basically what you're just doing is you're trying to figure out what you're going to identify U as. Normally it's inside of a function, but that just comes from practice. And then you're going to identify U and then find du by taking the derivative of U. And then, if necessary, you can multiply a constant, like it's going to normally be like a fraction or something to make it more easy to substitute du in. So you can get only u's and du's. Step 4, that is step 4. Step 5 is once you have a more simple function with u's and du's, you're just performing simple integration with the anti-power rule or any other rules that you might know of. And then you're just going to resubstitute x in for all the u values. Here's the example. I have what looks like a somewhat complicated function, the integral of 3x squared times x cubed plus 5 to the 10th. You kind of see that the inside function is x cubed plus 5. So you identify that as u. Du is just the derivative of 3x squared. And that happens to actually be the function multiplied to the u value. So then once you substitute u and du in, you get that this problem is just the integral of u to the 10th du. And you do the anti-power rule, and you come up with that answer by subbing in back for x.
All right, so 2.3 is a section about separable differential equations. A differential equation is an equation that contains an unknown function and one or more of its derivatives. So the steps in solving a differential equation, you must separate the variables to two different sides and make sure to leave all the constants on the one side just to make it easier when solving the problem. And once you have the constant on each side, that's gonna come after you integrate. So you have to separate and then integrate and then keep constant on one side. And then after that, you have to solve for y if you can, and if you get a natural log in your result in your answer, then solve for y. And if there's no natural log, solve for c or the constant. And absolute values are not necessary. Then at the end, plug in the initial condition if you are given one to solve for c. Here's an example problem. To find the general solution, and as you can see, there's a differential function as well as an unknown variable. And so the first thing that is done is separating the t and the m to separate sides, then integrating, then taking the natural log of m, multiplying by e on both sides, and then that cancels with the natural log on the left. You're left with m equals e to the 1/2 t squared. And then since e to the c is a constant, you can just note that you can change it to k. And that is your final answer for the general solution. However, if you were given an initial condition, you can plug in and solve for c as your constant.
So 2.4 talks about back substitution, which is very similar to u substitution, and there are 6 steps that go into solving back substitution equations. And so the first step is to notice that you are trying to integrate a product, and so this just means like looking at the integral and just identifying, what exactly you have to integrate. The first real step is identifying the inside function of the composite and calling it u. And so that is basically just discovering which function you have to integrate and take the derivative of in order to actually complete the integral. And so the second step is to take the derivative of u, and then the third step, if you have to, if needed, you multiply a constant inside the integral to create du and balance it out by multiplying the reciprocal of that constant outside of the integral. And so there are two parts of this step. The first part of step 3 would be to identify any extra x's, and then after you identify those, then to isolate them in the extra scratch work. And so after you do that, you head to step 4, which is to substitute u and du as well as the extra x's into the equation, and then perform your integration by the anti-power or the transcendental rules, and then resubstitute x back in for u. So this is best understood when you look at an equation, or at an example. So we're going to look at example 1 from the book, which you are trying to integrate x cubed times the function of x squared plus 4 to the 3 halves dx. And so your u in this situation would be x squared plus 4, but and then if you take the derivative of that, that would just be 2x dx. But then you're still left with that x cubed outside of there. So what you have to do is after you take an x out of that, you pull out an x from the x cubed to make the 2x dx, and you're left with an x squared. And you can solve for x squared by just solving, or like moving the x squared to one side and then just subtracting 4 from u, so that x squared is equal to u minus 4. And so after you figure out all of those substitutions, you just plug those into the equation and then multiply those out so it's all one equation, and then you perform the anti-differentiation. And then after you complete all of those steps, you substitute x squared plus 4 back into the equation, and then you're all set. And that's how you do back substitution.
With 2.5, we're learning about powers of trig functions with sine and cosine. And there are two cases of integrating with sine and cosine. And the easier and more often seen example on the AP test is when the power of sine or cosine is an odd number. One of whichever function has the odd power will be the du, and the rest of those functions can convert to the other trig functions by means of the Pythagorean identities. So it's important to remember the three shown right here: sine squared plus cosine squared equals 1, and 1 minus cosine squared theta equals sine squared theta, as well as 1 minus sine squared theta equals cosine theta. To figure out these problems, you need to manipulate these three different equations in order to solve the integral. Case 2 is when it's a little bit more of a difficult situation, when the powers are even. In this case, variations on the half angle arguments rules come into play. Therefore, you need to understand these three boxes of integrals in order to solve these equations, because these specific integrals that come out, it is important that you use these instead of the more easy Pythagorean identities. Those are both the cases, and it is important just to practice using the different equations to figure out how to solve depending on the different case that you're presented with in the problem.
Okay, so 2.6 is very similar to 2.5, except we are now dealing with secant and tangent. And so when you're going into this section, it's really important to remember those Pythagorean identities, that secant squared theta is equal to tangent squared plus 1, and so forth, as you can see on the screen. And also to remember the derivative rules, that the derivative of tangent u would be equal to secant squared u du dx, and that the derivative of secant u is equal to secant u tangent u du dx. And so when you're dealing with this section, you're going to be approached with 3 different types of problems, 3 different cases. And so the first case is when the secant or cosecant's power is even, then your u would be tangent x, and your du would be secant squared x dx. And with these kinds of problems, it's important to remember that tangent squared x plus 1 is equal to secant squared x. And so when you do your u substitution, then you can just add 1 to the secant squared, or to the tangent, in order to solve for secant. And so for case 2, that is when the tangent or cotangent's power is odd, then your u is secant x, and your du is secant x tangent x dx. And so you're solving for tangent squared x in this case, and so that is equal to secant squared x minus 1. Or after you do your substitution, that would be equal to u squared minus 1. And if you're dealt with a problem where the tangent's power is even and the secant's power is odd, then we do not have any steps that we can do at this time because this is not an integration by substitution problem. And you will learn how to do this in chapter 8.
Okay, so last section, chapter 2.7, is about slope fields, where you draw a small line with the slope of the function at each point in the Cartesian coordinate system. And the steps of sketching a slope field is to determine the grids of points that you need to sketch, pick your first point, note its x and y coordinate, plug these numbers into the differential equation. This is the slope at that point. Third step is to find that point on the graph. Make a little line or dash at that point whose slope represents the slope that you found in step 2. And then 4 is to repeat the process again and again. AP usually approaches slope fields in 4 ways. As the first one is to draw a slope field. Second one is to sketch a solution. Third one is to identify the differential equation. The fourth is to identify the solution equation. You want to start by finding the initial condition point on the graph. And then the sixth is to follow the marks from the slope field in either direction from your initial condition. So to find the differential equation for a slope field, horizontal dashes represent a slope of 0. Dashes to the bottom right represent a slope of less than 0. Dashes to the upper right represent a slope of greater than 0. And all dashes in any column that are parallel to each other, they have no y. And all dashes in any row parallel to each other has no x. And here's an example of what a slope field looks like.